So that is it for material on the exam. The class will, this is it. These are the last two lectures, knowing pharmacokinetics, that's really kind of ties all of this part together. So what I want to do now is just quickly, I already looked through the quiz, just go over a few questions. I have not looked in depth at everyone's answers. I just kind of screened quickly and pulled a few problems that seemed.
We're good.
I will release the quiz grades after class tonight. So, first question.
But I'm not sure. I don't remember if I picked the first one or not.
I picked the first one.
This
I know
is
I
a
picked the
drug.
second
It's also used as a standard
Are the grades
in
out?
mass spectrometry.
Wait, so he's gonna do after class.
If we looked at which of these statements are true, this first one is true because this has a pi system, so you're going to use a UV detector. Also true, reserpine would have at least 2 sharp peaks between this range. In fact, you could argue it has 3 because there's an olefin here, so that's the 2 ketones, the olefin.
It's not a secondary,
Looking at the IR, those would be there.
Yeah.
This one's the tricky
H2.
one.
I know.
The NMR of
It's
reserpine
like,
would have
no,
6 different
it's
methyl
right.
groups. It's actually false. It would only have 5. The reason is this structure here has a line of symmetry down the middle of it, meaning that this
This is
and
working.
this methyl group
You're looking at the
are the same.
But it's working. Like, if you, I'll send you some.
All of these other ones are different. All of these here, this methyl group and this methyl group are the same, and all the other ones are different. So in total, if my math count's correct, that would be 1, 2, 3, 4, 5 total, not 6. The final one is also not correct because
I don't know how to.
an amine shows up as a broad peak, so that NH2 shows up a broad peak. So when we looked at amine containing IR spectrum, I said there's fangs oftentimes. Each of those fangs correspond to one NH. So when you have an NH2, which is an amine, this is technically not an amine, this is an indole. Each of these are one of the fangs on the peak. In this case here, if you actually look at the IR of reserpine, it has actually a sharp, somewhat sharp peak for this NH, but that's not important.
The diagram, it says
Overall,
NH2.
the fact is that it's not going to have this type of
And they have a diagram.
this type of pattern because it's not, there's no amine molecule. There's a nitrogen.
I know, Boba.
So, next question, I have this one marked as wrong, it's correct, so don't worry. I looked at it, I made a mistake, it's already corrected on the exam. I was wondering why so many people were getting this question wrong, and then I realized it's not the right one. But, so, I didn't really actually need to show this. Pretty obvious that this structure here has 2 alcohols. Although this has alcohols here, what we're looking for is the carbonyls. This one has 2. Spectra A has these 2 gigantic carbonyl peaks, whereas this is not considered gigantic. They're pretty small. It doesn't have carbonyl peaks. The final NMR question, which I'll go over, is this one here. So why are these first 2 options incorrect?
Proton C is a double.
Arrow protons have a shift to the 7.
I think I got that one right.
Proton C is a double.
Proton C
It's a triplet.
will show up as doublets. So remember that integrals
No, you're right. It's a triple.
give you the number.
Like, I can see how.
Integrals give you the number of protons next to it. So if we looked at proton C, it has 2 protons next to it. So it would show up as a triplet.
Yeah.
So like you get either 0.5 or 0.3.
Proton B will have a higher shift than proton C. That is true because proton B is next to a nitrogen is more electronegative.
You lose 0.25 because you didn't.
And finally, the ratio,
because you didn't pick
if you
one right
integrate
answer.
these protons,
Because you picked
should be 1
wrong
to
answer.
2 to 2. There's no symmetry in dopamine here in this arrow, such this proton is different from this one and that one.
picked C as well. Then.
if you were to look actually at the NMR of dopamine, you would see 3
I don't know exactly what I did.
protons for these two. These would be different, they would show up as different. Okay? So, that's it for the questions I was going to go over on the quiz. The rest of them are pretty straightforward, I think, in terms of analysis. So, I think I had a couple questions a while ago about separations back from the first, lecture. And a request for more questions on this. So, this is a question I actually created last year. If we have these 4 structures, we should be able to develop a method to solely isolate each one of them based on the different structures. So, if we wanted to isolate the methoxyacetate, so this compound here, how would we go about doing that? If we dissolve both of these in an organic solvent, and what type of solutions do we need to add if we had a mixture of these 4 to isolate just this one? And so I'll give an example for this. There's 3 more on this slide I won't go over, but you should be able to work through those. So if you take these 4 compounds and we want to separate this one out, we have 2 options. We can add base, so sodium hydroxide or sodium bicarbonate, or we can add HCl. We go ahead and add HCl to this. What's going to happen is HCl is going to protonate amines. So it's going to protonate this amine and this amine. Amides will not protonate because their pKa is way too high. So what you end up with is a solution of the top compound, so this one here, and this compound here, in the organic, and the other 2 in the aqueous. So because these have amines, what's going to happen is that the amine will be protonated. Protonated species go into the water. So in each of these cases here, you end up with something that's protonated, so you are able to separate them out into the water. So now you have these 2 compounds in solution and you want to separate them, you can do a second extraction. So you can take these, and let's say you add sodium hydroxide. So what's going to happen is sodium hydroxide is a base. It's going to deprotonate acidic protons. So it'll deprotonate the carboxylic acid. This would end up in the aqueous, while this structure has nothing to deprotonate, and so it would end up in the organic layer, and you would end up with solely this structure. So if you were to get asked, okay, how do I isolate this top compound? You would wash HCl, take organic, wash sodium hydroxide, take organic, and there's your only molecule. If you wanted, and so you can go through for each one how you might go about isolating them pure overall. Okay, so I have 3 others here. If you want to work through at some point, you can. Also, a couple other things, since I didn't get any specific questions about things to cover, I threw in these from last year as well. How do we compare normal phase and reverse phase? So reverse phase is C18, our mobile phase is always water. If we wanted to increase the separation, of the compound, the resolution, we increase the concentration of water. Remember that increasing the concentration of water increases the more polar of the two. The more polar of the two options, and so the compounds, which have some nonpolar groups on them, want to interact with the nonpolar C18, and so they tend to stick more. Now, because of that, they separate more, but they also increase the time, retention time.
I can't do that.
Now, in general, reverse phase, we covered, it said molecules.
Yes.
And again, that's a relative term, because most drugs are polar, they have polar bonds, but it's better for the majority of drugs. So what we end up getting visually, if we look at, say, a trace, if we have, let's say, a concentration of, we're just going to call this concentration X.